Hello everyone, welcome to JCE Connect. In previous lecture, we have started module number 4, that is impact of jet on a curved vanes. There we have discussed about impulse momentum principle and some of the basic concept which are being using for the analysis of the hydrodynamic force. So in this particular lectures, I'll be taking some of the cases, uh, that is force exerted by a liquid jet on a stationary curved vane. So in this, as we know, we have to use the impulse momentum principle. Since the force is acting in a very short interval of time on the vane, and that force we need to calculate by using the impulse momentum equation. So what that equation says, that is a force in x direction is equal to the rate of change of momentum in the direction of jet. In whichever direction the jet is acting and also exerting a force, in that direction the momentum of the liquid get changes. So that is impulse momentum equation, that is rate of change of momentum in the direction of jet, that is given as mass flow rate into change in velocity in the direction of jet, which can also be written as mass flow rate. So as already we know that the mass flow rate can be written as rho q into bracket the final velocity minus initial velocity. You can write, or else you can write rho q into initial velocity minus final velocity. Okay, so that is mass flow rate into change in the velocity. Anyway, it gives you the change in velocity. So that is initial velocity minus final velocity on the basis of, so here on the basis of the type of curved vane or the plate and the direction of the jet striking the vane, the following three cases are considered. So here, what are those cases? The jet striking a symmetrical stationary curved vane at the center. Means if the jet is coming in this direction and hitting the curved vane at the center like this. So what is the force exerted by the jet? So the jet striking a symmetrical stationary curved vane at the center. When it hits at the center, then the water deflects in this direction as well as in this direction symmetrically. Okay, that is the first case. Second case, jet striking a symmetrical stationary curved vane tangentially at one of the tips. Means it just moving in this direction and this is the curved vane like this, but hitting at tangentially like this, or if this is the curved vane, if the jet may strike in this way tangentially to the curved vane at one of the tip like this. So why it is calling as symmetrical? So the whatever the angle with jet enters into the curved vane, so it is entering with some angle, say this is theta. So with what angle it is entering, with the same angle it may get out, it exits. If you take angle here, this is also theta. So this is called symmetrical case. The jet striking a stationary curved vane tangentially at one of the tips. So this is acting tangentially. It is entering with angle theta and leaving also with an angle theta. Okay, so these all cases are fixed cases. This is also fixed one. Okay, the third case, jet striking unsymmetrical stationary curved vane when the jet striking tangential at one of the tips. Means this is the curved vane, and it is a fixed one. How the jet is striking? It is striking tangentially at one of the tip. These are called as the tips or ends. Tip of the vane or tip of the plate. Okay, so this is the edges. it is striking at one of the tip tangentially. When it is striking at one of the tangential, it is making an angle of theta here. So it is making an angle of theta with the horizontal. So it will be entering with some angle theta, and again it will be leaving like this. It will be leaving here. So when you draw horizontal here, so it will be leaving by some other angle, say pi in previous case. So in this case, when the jet was striking at one of the tip, and it was entering with an angle of theta here, and it was leaving with same angle theta. See, it was entering with angle of theta here, and it was leaving with the same angle theta. It is called symmetrical case. But unsymmetrical case, what happens? It will enter with some angle into the vane, and it will leave with some other angle, say pi. So entry angle here is a theta, exit angle will be pi. This is unsymmetrical case. So these all cases are fixed case or a stationary case. When the vanes are stationary and the jet will be striking the vane, what is the hydrodynamic force it exerts, that we need to calculate it. So this is force exerted by a liquid jet on a stationary curved vane. So these are very important derivations. These derivations are very important. So for these all derivations, we use one concept, that is impulse momentum equation. So what impulse momentum says? The force which exerts, that will be equal to the rate of change of momentum in the direction of jet. Okay. So let us take the first case. So in the first case, so here I'm considering the jet striking a symmetrical stationary curved vane at the center. So consider this one. So consider a jet of water. So here I'm taking this is the pipe. The water is flowing through this pipe, and a nozzle is fitted at the end of the pipe. A nozzle is a gradual reduction in cross-sectional area. This is called a nozzle. The purpose of fitting a nozzle is just to increase the kinetic energy of the liquid here. Okay. Then when the water comes out from the nozzle, it will come in the form of a circular rod or a non-circular rod with a high kinetic energy. Okay. Then it comes and hits the vane, and it is hitting at the center. That is our first case we are considering. Jet striking a symmetrical stationary curved vane at the center. So we need to calculate what is the hydrodynamic force the jet is exerting on the vane. So consider a jet of water of diameter d moving with a velocity v. This is moving with a velocity v, this jet, and strikes symmetrical curved vane at the center. Repeating, consider a jet of water of diameter d. This is the diameter d moving with a velocity v, strikes a symmetrical curved vane at the center. So this vane is placed symmetrically, means the jet is striking exactly at the center. Whatever the quantity of water is moving in this direction, the same will be moving in this direction also. So with whatever angle it is been deflecting after striking, with the same angle it is also deflecting here. So here it is marked angle of deflection. It is moving, or it is deflecting at an, after striking it is deflecting at an angle of theta here. Okay. So when it strikes at the center symmetrically, which is shown in the figure, then we have to also consider that there is no loss of energy due to impact. So this is the assumption we have to make after striking the jet. After striking the jet at the center, there is no loss of energy. So this surface of the curved vane, this is inner surface of the curved vane, we have to assume it is perfectly smooth. It's very smooth. There is no any loss over here. There is no frictional loss here. whatever velocity with which the jet is striking, this with the same velocity it is coming out, v. So here I consider the velocity of the jet as a v. With the velocity v, it is striking at the center. After striking, the water will glide over the surface like this, and it comes out with some angle. And whatever velocity with which the jet is striking, with the same velocity it is coming out. So there is no loss here. So that is the assumption we have to make. That is, we have to also consider that there is no loss of energy due to impact of jet. And one more assumption we have to make: the difference in elevation between the incoming and outgoing jets are neglected. So this is an incoming jet and this is the outgoing jet. Incoming and outgoing jet, the difference will be same here. There is no any difference in incoming and outgoing jets. That is also one assumption we have to make. Then the liquid jet, after striking the vane, gliding over the surface of the vane and comes out with the same velocity v. Okay, so it is coming with velocity v here and striking at the center, then the glides over the surface and it comes out with the velocity v. When it is coming comes out with the velocity v, which will be making an angle of theta here. Okay, so theta here. Then we have to resolve this velocity. One velocity we get as a v sine theta and another we get as a v cos theta here. Okay, now let us solve this one. Then we have to write here the velocity at the outlet of the plate, the velocity at the outlet of the plate, velocity at the outlet of the plate can be resolved into the following two components. The first component is component of velocity in the direction of jet. In the direction of jet. So here, if you take the first component, the component of v, the component of v in the direction of jet is this one. So this jet is coming with a velocity v and striking the vane, and it is going out of the vane with same velocity v, making an angle of theta. When you resolve this one, we get two components. One in the direction of jet, other one is perpendicular to the direction of jet. So when it is coming in the direction of jet, both are parallel here, but it is in opposite direction. Okay, this is in opposite direction. V is, so one V is going in this way. See, the V is going in this way and the component of this coming out like this. So it is V cos theta. I hope you understood this one. Okay, so the component of velocity in the direction of jet, which can be written as minus v cos theta. The minus sign, why the minus sign? It is coming in the opposite direction. Negative sign indicates that the velocity of the jet at the outlet is in the direction opposite to the jet of the fluid jet. See, this is the velocity v striking the vane at the center and coming out with a velocity v, making an angle theta. When you resolve this one, we get in the direction of jet but in opposite direction, v cos theta. Okay. Second component, what we get? Component of velocity perpendicular to the jet. That is, we get v sine theta in y direction, this one. We get two components at the outlet. So this is inlet and this is the outlet, here outlet. So one v sine theta, another one is a v cos theta. Then we also the mass flow rate of liquid striking the vane. Also mass flow rate. This already we discussed mass flow rate, how it can be expressed. So about this I explained in previous lecture. Mass flow rate of liquid striking the vane means how much quantity of water is coming out of the nozzle here. How much quantity of water, that is called mass flow rate of water striking the vane. Mass flow rate. Okay, how much kg of water is coming out of the nozzle and striking the vane per second, meaning that is called mass flow rate. That mass flow rate is can be given as rho a into v. As we know, as I explained this one, density is equal to mass by volume. So what is mass? Density into volume. But mass flow rate with respect to time is also divided by time. We get density into volume by time is what? Q. This Q can be written as A into V. This is called mass flow rate. This is called mass flow rate. Mass by time. Mass by time. Now let. So we want here hydrodynamic force in x direction. Let Fx and Fy, two forces we want in x direction as well as in y direction. So here this we take it as a Fx in x direction, Fx, and perpendicular to that we take it as a Fy. Let Fx and Fy be the force components exerted by the liquid jet on the plate in the direction and normal to the direction of jet. Normal to the direction of jet. So let us take this Fx and Fy are the two forces. One is acting in the direction of jet, other one is acting in the direction normal to the jet. So the jet is coming in this direction and hitting the vane. So this exert a force in x direction. Let us take that force as a x, that is Fx. Other one force is Fy, perpendicular to the vane. So these two forces we need to calculate here. Okay, so that way to consider Fx and Fy be the two force components exerted by the liquid jet on the plate in the direction of the jet, one force, and normal to the direction of jet will be another force. Okay, then next, then applying the impulse momentum equation. Now you apply impulse momentum equation. Impulse momentum equation. The force exerted by the jet in the direction of jet. In the direction of jet means we to calculate fx is, that is fx, we want force in x direction exerting by the jet. So here the water is coming out of the nozzle with a velocity v, and this jet is having a diameter d, and it is striking the vane at the center. Then after striking the jet this water glides over the surface and leaves the vane with a velocity v, and while doing this it exerts a force in x direction as well as in y direction. So we have to calculate what is the force exerting by the jet on the vane in x direction. So to calculate that force we are using the impulse momentum equation. So what that impulse momentum equation says, Fx equal to rate of change of momentum, rate of change of momentum in the direction of jet, in the direction of jet. So in whichever direction the jet is acting, that direction the momentum to be considered. That Fx will be what? Mass flow rate into change in velocity, because we know momentum equal to mass into velocity. Since we are taking impulse momentum equation, so that is Fx equal to mass flow rate into change in velocity. Then mass flow rate, as we know how to write, rho into a into v. Change in velocity means initial velocity minus final velocity. Then this can be written as it is, you write initial velocity of the jet. How much is the initial velocity? V. So the jet is striking the vane at a velocity v initially. Then after striking, it leaves with a velocity v, but we want in x direction. So initial velocity will be v minus final velocity minus of minus v cos theta. Why minus of minus v cos theta? Look here in this figure, it is striking with a velocity v, that is the initial velocity, and it leaves with velocity v by making an angle of theta, but we want in x direction. The x direction is what? V cos theta, but acting in opposite direction, that is minus v cos theta. I hope you understood this one. Then finally what we get? Rho a v, we get v plus v cos theta. Finally we get rho a v square 1 plus cos theta. This is in x direction. This is equation. Then another one is second one. The force exerted by the jet normal to the direction of jet, normal to the direction of jet, that is we want force Fy. So Fy, again the same formula, mass flow rate into change in velocity. The mass flow rate, what? Rho a into v, change in velocity, initial velocity minus final velocity. Then again rho a v. So what is the initial velocity with which the jet is striking? In y direction we want. So is there any velocity acting in y direction initially? No, there is no velocity acting in a y direction. So initial velocity is 0 minus So what is the velocity in y direction? This is v sine theta. I hope you are understanding this one. So here there is no velocity acting in the y direction initially, but there is a velocity, that is a final velocity in y direction at the exit. So this is v sine theta minus v sine theta. So we get rho minus rho a v square sine theta. This is Fy. So the negative indicates the force is acting in negative y direction. Okay, finally means it will be acting downward. Finally the resultant, how the resultant can be given? The resultant will be what? Root of fx square plus fy square. This is the resultant force. And the direction, this is the magnitude, and the direction can be given as theta equal to tan inverse of fy by fx. Finally, so how it can be represented? So if the value of f you are getting one value you get a positive, this is fx, and another one is get fy. The resultant of these two will be which one? This is f. Okay, which is, this is angle theta. This is final representation of force. Okay, so this is the resultant of jet acting. Okay, I hope you understood this one. So please practice this derivation, and I hope you understood this one. And also remember, you have to apply the impulse momentum principle here. Impulse momentum principle. So first thing, you have to draw a figure neatly, that is a pipe and a nozzle, how it is acting and which case is being given, whether it is a symmetrical case or a unsymmetrical case. Let us find out that, and then according to that you draw the figure, then you calculate the force exerting by the jet. Okay, so this is a symmetrical case, that is a jet striking at the center of the vane. So in next case we'll take, that is just striking at one of the tip of the vane. So next case, so next lecture we'll take this case. This is jet striking at one of the tip, and the jet vane is placed symmetrically. Okay, so this case we'll consider and we'll solve. Okay, thank you.